All right, the last two circuits of the year are going to deal with the LC circuit, an inductor and a capacitor in series. So we have here a capacitor of capacitance C and an inductor of inductance L. All right, the first one that we're going to do is with the battery. So the battery is putting charges on the capacitor and it's forcing current through the inductor. Okay, I want to go ahead and do another Kirchhoff loop rule. So the first thing I need to do is put my plus and minus on each of the circuit elements. I know that this plate of the capacitor is going to receive positive charges, so it's going to be at a higher electric potential than the other side. So as I go clockwise, that's going to be a drop. When I go to the inductor, well, what does the inductor want to do? Is it going to align itself with the battery, or is it going to oppose it? Of course, if we think about what the inductor wants, it wants to oppose the change in flux. So it's going to go in the opposite direction of the battery. So if I go clockwise, the battery is a voltage gain, the capacitor and the inductor both are going to be a drop in voltage. So I can set up the loop rule, epsilon, the voltage gain of the battery, minus, because the capacitor is a drop of Q over C, and again, minus for the inductor because it's also a drop in voltage, and that is L di dt, and all of these voltages have to add up to 0. Great. So I'm ready to set up and solve this differential equation. I need to solve for the derivative, but I'm noticing that my small factor of di and dt do not match any of the variables that I have in the equation. The only variable I have is right here, charge, because I know that as the capacitor charges up, the total charge on it is going to change. Epsilon is just the voltage of the battery, capacitance and inductance are also constants. So somehow I've got this variable that doesn't match any of the small factors. But I do remember that current is dq dt, the derivative of charge with respect to time. So what I'm going to do, I'm going to cheat a little bit. I'm going to take the derivative of this entire equation with respect to time. Well, the derivative of epsilon, since epsilon is a constant, is just 0. And then minus 1 over c is also a constant, so I can pull it out of the derivative, and I'm left with dq dt minus L, which is also a constant. And then what happens when I take the derivative of current? I get the second derivative with respect to time, and all of that is equal to 0. Great. So I'm ready to solve for one of the derivatives. But I have two derivatives up there. So what I need to do to match the small factor to the variable is I need to rewrite dq dt as I, the current. And now one of my small factors matches the variable I. Okay? So I'm going to go ahead and move the derivative to the other side. So I get minus 1 over c times the current is equal to L times the second derivative of current with respect to time. And I want the derivative all by itself, so I'm going to remove the L by dividing it from both sides, and I get minus 1 over LC times the current is equal to the second derivative of current with respect to time. So this is now a second order differential equation. The second derivative of something is equal to minus some constant times that something. This is something you've seen before. You should remember this equation. What functions can you take a derivative of twice and return that function, but now with a negative? Right? Of course, these would be trig functions like sine or cosine. This is the condition for simple harmonic motion. We saw this back in mechanics. When you take the second derivative of something and returns negative of that something, then the solution to this second order differential equation is either a sine or a cosine. So I'm going to write what we had before in mechanics, and that was minus omega squared x is equal to the second derivative of x with respect to time. Okay, great. So that makes this whole term in front of current, in front of my variable, that is omega squared. So omega squared is 1 over LC. That means omega is 1 over the square root of LC. And furthermore, if I want to find the period, I know that period is 2 pi over omega. So that would mean the period of oscillation of this LC circuit is just 2 pi times the square root of LC. Okay? So what does that mean for this particular circuit? A battery in series with a capacitor and an inductor. The current is undergoing simple harmonic motion. So that means the current as a function of time is equal to some maximum value times the cosine of omega t plus phi. Okay? But remember, from that second order differential equation, we identified what omega is. So this current as a function of time is just I max times the cosine of 1 over the square root of LC times t plus phi. Okay? And I want to address this phi right here on the end. Remember that phi is just a phase shift. And it says if I have a cosine or a sine function with a phase shift, it just moves my entire function left or right. So I've used cosine as the solution to this second order differential equation because that's what we did back in mechanics with something like a pendulum or a spring mass oscillating system. And the reason we did that is when it was cosine, it's because typically you start at an amplitude. And when t equals 0, cosine of 0 is going to give you an amplitude. It's going to give you 1, right? But I want you to think about the LC circuit, right? At t equals 0, at the beginning of time, when you first connect this circuit, the capacitor is like it's not even there, right? The capacitor allows charges to flow freely, so the inductor is going to be very good at opposing the battery. And it also means that all of the voltage of the battery is on the inductor. So the inductor is really doing its job. It's trying to shut down the current. So that means for the LC circuit that the current is 0 at t equals 0. The current is 0 at t equals 0. So some might say that maybe for example, a sine function would be a better solution to this second order differential equation because at t equals 0, sine of 0 is equal to 0. But I'm choosing to leave it as a cosine and just put in here a phase shift. So I would say the current as a function of time for an LC circuit with a battery is just some maximum amplitude, some maximum current times the cosine of omega times t plus a phase shift. And how do I make a cosine look like a sine? Well, I phase shift it by pi over 2, meaning I take the cosine function, right? Cosine starts at 1, and I just move it over by pi over 2. And that makes a cosine look like a sine. Okay? So this is Mr. R signing out from the LC circuit. And I want to ask you, did you hear the one about the man who was frozen to 0 degrees Kelvin? Okay, this is Mr. R signing out. I just wanted to ask you, did you hear the one about the man who was frozen to absolute 0? It was pretty tragic, but he's okay now.